Lovely. Okay, we're on to the next section in your book. As you see, following the indices, we now come to the next section headed logarithms. Okay, now logarithms might be a bit old-fashioned, but they're very useful when you come to simplify more complex calculations, and they're a form of an indices. So what I've started with there is this 2 cubed we know is 8, because this is 2 times 2 times 2, so we know that that is 8. That's correct. Now when we're using logarithms, what we can do, and I tend to jump straight into this, is this, and I show students this way. Taking logarithms of both sides. Now of course in your calculations you don't have to keep writing this, but you just remember this. Alright, and this is what we do. Now when we take logs of both sides, the power comes down and multiplies. So this can be log 2 equals log 8. So 3 log 2 is equal to log 8. Now there is a question on your calculator here. You see, hang on, let me look at my buttons. Now I've got one button which is the typical log button, but the next button to it is LN. Okay, now this log button is base 10. In other words, the reference number is base 10. Okay, but this one is the natural log, base E. And E is just a constant Euler's number. I think it is 2.718, but you don't need to remember that unless it comes up in a lecture. So on the calculator you've got 2 buttons. It doesn't matter which one you use because they'll both give you the correct answer, but you do need to use the same log or ln on both sides. So see, I've written log here, so this would imply it's log base 10. Log base 10. Now let's check this out. We can work on the calculator. Log base 10, 2. What does that equal? Well, here we go. Turn this on. 3 times log. Alright, and now I put the 2 in. Close the brackets for good practice. And that equals my answer, 90308. So I'll round that off to 4 decimal places. Becomes 0.9031. 0.9031. That's that side. Done. Okay, let's have a look at this now. Log base 10 8, we can put this straight in. Log base 10 of 8, there we are. Close the bracket for good practice, equals bingo, straight away. Alright, 9031 to 4 decimal places. So these are completely and utterly identical. You'd expect them to be. Now, the calculator is geared to give you the answer. It follows BIMDAS, and if you've got log here, it implies that it's base 10. So let me show you this again. Turn it on. When I hit the log button, notice carefully it's log bracket. In other words, the 10 is implied. So the calculator shows you the difference. Log is automatically in base 10, and you use that a lot. Now let's do the same problem, but we'll use the one next to it. So if this is correct, alright, I should be able to say, right, taking logs of both sides, 3 log ln 2 must equal the natural log of 8. Now the ln function is used. It's not base 10, it's base e. Now let's have a look at this. So 3 times, now I'll use this one, ln. Okay, notice there's an ln there, so we're in exponential, log base e, and I put the 2 in, close the bracket for good practice, and this now equals, this side equals 2.0794. Alright, and I'll just take it off to 4 decimal places. What will this one equal? Let's have a look. Right, ln 8, close it for good practice, equals the same, 2.0794, which is what you'd expect. Okay, so there we are, we get the same answer there. That's pretty good. So all you have to remember is when you try to work these out, this is a very easy example, you see, which is what we start with in the book, very simple. But if you take it to base 10, then the left-hand side should equal the right-hand side. When you work it through, it does. If you take it to natural log, it's a different base. Okay, in other words, a different reference. You're using a slightly different base, but if you do the same to the left-hand side and the right-hand side, that will give you the same answer as well, and that's shown there quite clearly on your calculator. Now, sometimes, very rarely, your lecturer might ask you to work in different bases. Okay, but if you have a look on the bottom of that page, right, look at this a little bit. Although any base can be used, we commonly use E, that's natural log, and base 10 as bases, because those are the two that we have buttons for quick calculation on your calculator. Okay, now let's do a fairly straightforward one. The next, I'll just turn over, and the next example that we see is, can we evaluate log base 2 32? Now first of all, students will look at that and say, oh, hang on, it's base 2, so it's not base 10, it's not natural log. Can I do it? Well, as I've written out there, this one is fairly straightforward, because watch, what we do is we say let x equal log base 2 of 32. So that now means, from the previous information, this is the base, this is the power, and this is the answer. So we're using base 2 to this power to give us this as the answer. Now this is useful to remember, this little relationship. So now from this line I can go to here. I can say 2 to the power x equals 32. Now people are happier with that because there's no logarithm here, and they can usually work this out. Why they can work it out is because 2 is a factor of 32. So if I break this down, 32 now becomes 2 2s are 4, 2 4s are 8, 2 8s are 16, 2 16s are 32, which I now replace, as I showed you before, by this method. So now we have something very simple. All this becomes 2 to the x equals 2 to the 5. Therefore, x must equal 5. Okay, nice and simple, very straightforward. Logs can be simplified by using the 3 laws of the logs. So if you have a look at these, we've written them down for your benefit like this. Okay, so the first law is, if they're multiplied together, you can actually add the log of this. Here's an example, the log of 5 plus the log of 4. 4 5s are 20 according to this, and this goes into the calculator under log, and it gives you the answer. Similarly here, if they're divided, then you minus the 2 log forms, okay, and 20 over 3 will give you 20. Log of 20 minus log of 3. Again, put that into the calculator, and it drops out. This one as well works out quite simply. So if it's the log of base 3 to 5, this is 5 times log of 3 to base 3, and if it's the log of a number to the same base, log of 3 to the 3 is 1. 5 1's 5. This is an easy one. It drops out quite nicely. Okay, so the rest of these examples, using those 3 rules, work out quite nicely. We can rewrite these problems very simply, okay, in terms of addition or division. Now, using this idea, let's have a look at this one. Here's the next problem I want to show you. We have to find x, but we're given this little statement, 1 plus e to the 2x equals 4. Okay. Now, this is how we write it out in the book. I've got it written out like this. The first line, we can do a little bit of transposing. E to the 2x equals 4 minus 1, which is 3. I simply take this across. Remember the rule that we've done before. Change side, you change the sign of the operation. So now we have e to the power 2x equals 3. This is as simple as we can get. Now we take logs. So I'll write this in, and when you come to revise this, this is what you think in your head. You don't necessarily have to write it in unless the examiner or the lecturer requires you taking logs of both sides. It's at this point we do it. Now the question now is, which log? Which type of log? In other words, is it log base 10 or is it log base e? In other words, ln. Well, convention normally suggests that if we're dealing with if we're dealing with e, the exponential term, we'll use ln. It shouldn't really matter, because if you do the same to both sides, the equation is balanced. So, using this one, okay, this is what we get. Taking logs of both sides, we will have 2x multiplied by natural log base e equals natural log base 3. Let's have a look for the minute. Remember, this power comes down, multiplies the log term here, and we need the log term here. Now, the great thing about this, if we use ln when we're using e, then this is the base. The e base here is the same as the term here. So this, in fact, cancels out. Log, natural log base e, multiplied to the term of e is actually 1. So on this side we get 2x times 1, which is 2x, okay, and then we've got natural log base e3. So finally x will equal natural log base 3 divided by 2. Now let's just put that in the calculator just to show you what's going on. So natural log, there it is, ln, we put 3, okay. Now we close that off for good practice. All right, divide that by 2, and hopefully there's your answer, 0.549. Oop. Sounds like the ice cream man has come in. That's very good. There we go. And so the calculator gives us the final answer. So this is a useful technique if you remember to do this. Okay, when we're using the letter e, the exponential term, this is Euler's, I think it's actually Euler's constant, e, it's the exponential term. Okay, so it does actually have a value. Let's have a look at the value. So if I do shift, there we are, e, and put 1 in, close the bracket for good practice, this will tell you what e is, 2.718281828 blah blah blah. Okay, so we just probably round it off to 2.718 is fine. All right, that's the value of the constant. Just in case, let me show you the information here. Just in case you need to change base ever, here is the log conversion formula. So whatever the base is here, okay, you can change it to the new base, so b will be either 10 or natural base e, and then these two terms go above and below. Let me give you an example. There's one just shown there. So supposing the lecturer gives you this, okay, log base 7 of 23, what is that going to be? Now, it effectively means this. If we call it x, if we let that equal x, then we can say it's 7 to that power equals 23. Okay, so now we can do it. All right, so the solution here becomes quite straightforward. X, let's use log base 10. Okay, I like that. That's kind of nice. Equals log 23. So x now becomes log to base 10. We won't bother putting that in because we know it's log, as opposed to ln over log 7. Okay. Now, in comes your calculator. Turn it on. Log 23. Close it off. Divided by log 7. Close that off for good practice equals, there we go. And the answer in the book is 1.61. I've just written it to 2 decimal places. So if your lecturer or the examiner puts a problem in like that where you've got a different base, don't panic. All right, remember you can only use on the calculator log base 10 and natural log, but using this little technique here, you can actually calculate any base. it is not a problem. Okay. Now, would it work if you took natural log using natural log? Would that work? Okay, let's check it out. X ln 7 should equal ln 23, so that x should equal natural log 23 over natural log 7. Okay, hopefully it will, but let's just check it out. It's a different base, but we've used the same base on both sides. So natural log 23, close off for good practice, divided by natural log 7, close that off for good practice. Bingo. All right, really good. So you can see now, you can have full confidence in the fact that it is irrelevant whether you use log base 10 or natural log, providing you use the same on both sides. Don't do this, for example. Don't say, oh, right, I can say this. X log base 7 equals natural log, and there's an inconsistency. You're using log base 10 here and this natural log, so no. If you choose one, it's got to be both sides back there. Choosing this one, both sides back there, and the answer will, in fact, drop out to be exactly the same on both sides. And that's what you would expect to happen. Okay, so that's good practice. Right, on the next page, we've got a little heading here, solving exponential equations, and it asks you to consider the following problem, 4 to the x. Now, we've partly done this a little bit of revision, not too bad. So you think, okay, this is not bad. Is 4 a factor of 64? Yes, it is. So let's have a look. 4 4s are 16, 4 16s are 64. Great. So I can rewrite that in that manner. So finally, I can get the very simple answer that this is true, and therefore, as it shows in your book, x is equal to 3. So we consider this to be very easy. It's easy because 4 is a factor of 64. And those of you that are good with maths will see that straight away. So this can be done without the use of a calculator. Now, in real life, sadly, it's not always that easy. Okay? So sometimes we have more complicated situations, but this method is also good for anything. Watch this. This following method. If I say 4 to the x equals 64, I can still say this. Taking logs of both sides. Now again, you don't necessarily write this, but you can think this. Watch this. The x comes down. Here we go. And I'll use log base 10 because these are just straightforward numbers. So it doesn't matter. 4 must equal log base 10 of 64. Would that be true? Let's hope it is, because then when we rearrange this, we get this. X equals log 64 over log 4. Again, bring in the calculator. Here we go. Log 64, close off for good practice, divide by log 4, close off for good practice, and you get the answer 3. Well, that's good, because that's what we got up here. Now, why that's important is because sometimes this can be a bit awkward. Okay, it may not be as simple as that. For example, I've brought one here to show you, and this is rather nifty. Now, if I have this, 2 to the x equals 32, straight away those of you will say, aha, that I can do the easy way. Why? Because 32 is going to be 2 to the 5, isn't it? 2, 2's are 4, 8, 16, 32. In other words, 2 to the 5, and straight away you identify the power x as being 5, and you get it right. Okay, what happens now if I give you something like this? 2 to the x equals 35. All right, think about that for a minute, and we'll just swap this over. Let's rewrite this. 2 to the x now equals 35. Okay, straight away, the easy method won't work, all right? 2 is not a convenient factor of 35, but you say, oh, I remember taking logs of both sides, so taking logs of both sides. Again, you think this is what you do. Bring the x down, and log 2 must equal log 35. Here we go. This follows because we've found out the rules, we've used the method here. X log 2 equals log 35. So therefore, x will equal log 35. Remember, it's base 10. We don't have to put that in, but we do recall that it's base 10 log 2. Okay, now we bring in the calculator. Open it up, and here we go. Log 35, close it off for good practice, divided by, where are we, log 2, and close that off. Okay. The good thing about the Casio, this is the Casio, as you notice, it's an FX 82AU plus. I'll just write that in case you didn't realize, and it's preferred by the college here, FX 82AU plus. It's very good. Why I like it is because, as you notice, it always prompts, it always will prompt with a bracket. All you've got to do is remember to close it off at the appropriate point. So now let's see what this equals. Here we go, 5.129. Okay, so let's write this out, 5.12830017. Well, you might think, are these figures really useful? They just keep running on. What this means is this, that x to this power 283017 will actually equal 35. If you round this back, then of course at some point it won't equal 35 exactly. Now let's just check. We can do this in reverse if we're careful. Watch. Turn it on, and we'll use this little button here. Okay, this is your power button, so this is going to be 2, and we'll hit the button there. So we want 2 to raise to that power. All right, so let's type this in 5.129283017. Okay, and I'll close it off, equals, spot on, 35. So when x equals 2, this power here will raise the 2 to 35 exactly. There's an interesting question, of course. How far do you drop this off so that it doesn't equal 35? Well, let's try. Normally we work to 3 or 4 decimal places. Let's see what happens. See how good the calculator is. 2 raised 2, and it opens a bracket. Here we go, 5.12928. So we've got 5 significant figures. Let's round it off there. Ha! Here we go, you see. So if we curtail the power, if we drop it off there to 5 figures, we don't quite get the whole answer. We need all of it to give us, but that's probably close enough. You see, you'd round that off. You'd say, well, 34,9999. Yes, okay, that's close enough to 35. Within practical limits, it's not too bad. But it just shows you the effect of cutting off some of these numbers, rounding off at random. So does that bring in another rule? It does. The basic rule is this: do not round off until the very last step. In other words, keep all these figures right the way through, and you shouldn't have too much of a problem. But if you do have any difficulties, then of course go ask your lecturer, and they will guide you. Let's try one more just to show you this one. What happens if I ask for this? 7 to the x equals 40. Now, 7 is not a factor of 40. Okay, if it was 42, all right, you might be a bit better. All right, if it was 49, it would be better still. But you say, it doesn't matter, I can work this out. X log 7 equals log 40. Again, you go through the same rigmarole, the same pattern, log 40, log 7. Plug it into your calculator, and I've just done it very quickly here. 1.8957. So therefore 7 to the power 1.8957, and there'll be a few other figures because I've actually rounded this off, will equal 40. Okay, so it doesn't matter what the base is, really. You can use this little technique to change base, and you're using base 10 or natural log base e. That's quite handy as well. Let's get rid of that. Okay, let's have a look at this next one now. I'll just show this on the paper. We've just basically done this little one, showed you the method. We'll use the same method for something that's a little bit more complicated. So in the book, the next problem that they ask you for is this one. So see how we go. Can we solve for x when we've got this 2x minus 1 equals 28? Okay, so again, let's work this out. Now again, you can use base 10 or natural log. I'm going to use natural log here, all right, just to change it up a little bit to show you that you can use either. So taking logs of both sides, again, you think this is what we put down, okay? This is the power, so down she comes, 2x minus 1. Now, ln 3 equals ln 28. Have a look at that. I'm using natural logs here, just for a difference. I could use log or natural log. This case, I'm using natural log because I used the logs in previous examples. So let's see how we go. The next line then becomes this, equals, now ln 28. This comes across, it multiplies here. I change side, change sign, so that becomes that. 2x now equals ln 28, ln 3. Okay, minus 1 here becomes plus 1 there. And then I can work this out in the calculator. Here we go. I'll show you how to put that in. You probably know by now. So we're using ln 28. There we go. Close it off for good practice. Divide by ln 3. Close that off. Okay. Now that will equal that plus the 1 equals that 4.033. So 2x equals 4.033. I'll just round it off there. So to get x, I just divide that by 2. Bring back the calculator, divide by 2, bingo, 2.02 is fine. And that's the answer that's given in your book, rounded off to something that we can actually use.